So when we were outlining our strategy for deriving the backpropagation equations, our first step involved finding a generic expression for the derivative of the cost function with respect to a weight going from layer L-1 to the output layer, then a generic expression for the partial derivative of the cost function with respect to a weight going from layer L-2 to layer L-1. And that's what we've done thus far. So we have these expressions right here. And then in order to find a generic expression for any weight derivative, our intention is to use some recurring pattern as you compute derivatives moving backwards from layer to layer starting at the output layer L. And just to make this pattern a little bit more apparent, we're going to add another generic expression, which is the partial derivative of the cost function with respect to a weight going from some hidden layer L-3 to layer L-2. Now, the further you backtrack into the hidden layers, the more intricate the derivative becomes. So we're going to stop here, and we haven't shown how we arrived at this result, but I encourage the viewer to try to tackle this derivative right here. But now we get to the more interesting part of backpropagation, because when you examine these partial derivatives, you may notice that certain terms are reappearing. For instance, we see that if we take this term right here, at the point where the summation index variable is equal to v, that is I is equal to v, we get this exact term right here. And we get this part if we find a partial derivative of the weight going from u to neuron v in the output layer. Now, if we have, for instance, started at the output layer and stuck to the output layer and computed every single weight derivative at the output layer, that means that we have this product right here for every single v, which means that we have all these products in the second expression for the weight derivatives at layer L-1. So by computing these again, we're really only repeating ourselves. On a similar note, it seems as if this expression right here has a lot of resemblance to this expression here. In fact, if we just look at this part and we set j equal to v here, we get this exact expression right here. So if we apply the same line of reasoning and assume that we remain at layer L-1 and we compute the derivatives of all weights incident to layer L-1, once we get to the next layer, for a given I, we already have all these terms as we loop through them using index variable j. So if we were just blindly computing derivatives starting from layer L and then going to layer L-1 and then layer L-2 and so on, we will be repeating the same calculations over and over again, which seems like a waste. It would then behoove us to keep track of calculations we've already made so that we can reuse them instead of repeating them. In the introduction to the video series, when we introduced backpropagation and its purpose, it was mentioned that all backpropagation is an efficient way to calculate all these derivatives. And the engine behind its efficiency is the fact that we are reusing calculations we've already made. If we find ourselves at layer L-1, instead of computing every single term required to get to this derivative, we can reuse calculations from the previous layer. And we can do this at any given hidden layer. We can always go to the layer ahead of it and reuse some of its calculations. So this is how we're going to do it. We're going to define intermediary terms which will act as stores of previously made calculations. So for layer L, we'll define such term as delta I L, which means that using the same sort of notation, we're referencing the ith neuron of layer L, the output layer. And this will be equal to the partial derivative of C with respect to the activation at neuron I times the derivative of neuron I. The activation at neuron I with respect to the weighted input. Now we're going to substitute this delta term back to our partial derivative with respect to a weight going to a neuron in the output layer. So in this case, if this delta term indexes I, then if we let I equal to V, we just get that delta V is equal to the partial derivative of C with respect to the activation at the VF neuron times the derivative of the activation at the VF neuron. So if we substitute this part into this expression, we get that the partial derivative of C with respect to WVL is equal to delta V times the activation at the youth neuron at layer L minus 1. So this means if we compute delta I for every neuron going from 1 to n, then we have the means to calculate every single weight derivative going from some arbitrary neuron U in the L minus 1 layer to neuron V in the output layer using the delta term. Now for layer L minus 1, recall that a weight derivative going to layer L minus 1 was given by this expression. And since our goal is to reuse calculations from the previous layer, we're going to try to reuse the delta I terms. So we see indeed we can substitute for delta I here. And then we get that this derivative is equal to the sum as I goes to 1 to n of delta I times W VI L times the derivative of the activation at neuron L from layer L minus 1 with respect to its weighted input times AU L minus 2. Just realized I forgot to add the layer index for the delta I terms. So I'm just going to do that quickly. Now, just as the delta I terms from the layer L, the output layer, allowed us to reuse calculations made in the output layer in layer L minus 1, we need to define another intermediary value store here in layer L minus 1 such that we can reuse that in layer L minus 2. And so our new intermediary value store will be like this. Notice here that this term can be taken outside of the summation because this term does not depend on the summation index variable. It's a constant throughout each iteration of the sum. So let me just write this as AU L minus 2 times the sum from I goes from 1 to n of delta I at the output layer, because we're reusing calculations from the output layer, W VI L times the derivative of dA V, the activation at the V neuron with respect to the weighted input. Now, if you consider this part of the sum right here, it reappears in the derivative calculation at layer L minus 2. And in addition, this part has already been computed. So let's try to take advantage of that somehow. Going back to our derivative calculation for layer L minus 1, let's define a new intermediary value store as delta V of L minus 1. And to generalize a bit, we can state that the delta term for any arbitrary neuron J at layer L minus 1 will be the sum as I goes from I to n of delta I, L, and the reason I've used J as a subscript here is because the I has already been used for the delta terms in layer L. And this will be multiplied by the weight from neuron J to neuron I in layer L, and then multiplied by the derivation of the activation at neuron J in layer L minus 1 with respect to the weighted input at neuron J at L minus 1. So when I'm calculating the delta terms, the intermediaries for layer L-1, reusing the delta terms from the previous layer, that is the layer before it, at the output layer L. So this means I can rewrite this derivative as delta V L-1 times the activation at the youth neuron in layer L-2. So we've shown that in order to find the partial derivative of the cost function with respect to a weight going from neuron U to neuron V in layer L-1, we can first compute a delta term for neuron V, where we insert V here for the subscript, and where we reuse delta terms from the previous layer. So let us now examine layer L-2. And as we saw previously, the partial derivative of the cost function with respect to a weight going to layer L-2 was given by the following expression, and I'm just going to copy paste it to avoid writing it out. And since our goal is reuse, we're going to try to reuse the delta terms we computed at layer L and layer L-1. So we saw, for instance, that this part right here, this product, is given by the delta I term at layer L. So we can substitute that in. That is, this delta I term appears here. So substituting that gives us that this derivative is equal to the sum as I goes from I to n of delta I at layer L times the sum as j goes from 1 to n of, and I'm just going to copy paste these terms again here. Now what we can do here is to switch the position between these summations, in which case we get that this summation becomes the outermost sum, so as j goes from 1 to n, and this summation becomes the innermost sum as I goes from 1 to n, and we get delta I L multiplied by the rest of the terms. And just as a side note, when we go from step 2 here to step 3, and we're flipping the positions of the summations, we can sort of show here how this is algebraically consistent. If we take two nested sums of this structure, we can flip the summations and get a nested sum containing the product of our summation terms. Now, if you go back to our derivative, we see here that this sum, the innermost sum, is already given by the delta j term at layer L-1. Now, if you were to find the weight derivative for a weight going to layer L-3, we would, just as we've done previously, look for a delta term at layer L-2 to try to reuse that at layer L-3. So for layer L-2, our delta term for this particular derivative would be given by this summation right here as delta at neuron V at layer L-2. And now we would repeat this for any neuron K in the L-2 layer. That will be equal to the sum as j goes from 1 to n, delta j at the L-1 layer, times the weight going from neuron K to j at the L-1 layer, times the derivative of the activation of the kth neuron at layer L-2. And we would do this for every k going from 1 to n, that is for every neuron in layer L-2. And if we do that for every k, and we see here that in order to compute delta terms at layer L-2, we need to know the delta terms from layer L-1. So we are in fact reusing the delta terms from layer L-1. And if we did this for every single k, we would have the means to find any weight derivative going to layer L-2, as this derivative will just be given as delta V for layer L-2 times the activation at the youth neuron at layer L-3. So if we have computed the delta terms for every k going from 1 to n, which will include V, we will know this delta term right here. So let's summarize the usage of these delta terms